Welcome to Assignment-2 solution key. So the first question, which one of the following are Qiskit runtime primitives currently available on the IBM Quantum platform? The options are A and B. A sampler, B estimator. Question number 2, according to the IBM Quantum Composer documentation, which version of OpenQASM is currently supported for writing quantum circuits in the code editor? So the correct answer is option 2, OpenQASM, Open Quantum Simulators 2.0. Which statement correctly describes the difference between sampler and estimator primitives in Qiskit? The correct answer is the first option. Sampler returns measurement outcome distributions from a circuit, while estimator returns expectation values of specified observables. Question number 4. This is a little bit tricky question. In the transpilation process, which of the following steps are not performed to prepare a quantum circuit for execution on real quantum hardware? So they asked not performed. So the correct option is fourth option, converting all gates to HUD and C0 gates only. So this is not performed. The remaining three, decomposition of multiple qubit gates and mapping logical qubits to physical qubits and optimizing circuit depth to reduce gate count will be performed. Only the fourth one is not performed. Next, fifth question. So from here onwards, I have seen many solutions in the YouTube. They have given wrong answers completely, which will reduce your score. So please follow from here. So I have done all these things on the circuits, and I will show the each solution for the circuits also here. So what they ask is, using IBM Quantum Composer, create a 3-qubit starting in state 00, apply a rotation gate R by 5 by 3 to the first qubit 0. So let us see what happens if this is taken. So here we have taken three, so we are going to take 3 qubits. So that's the reason I am deleting this one. So now we had q0, q1 and q2. Right, now we have taken R by gate, and here we are going. So what was the rotational axis they have given? R by of pi by 3. The angle given is pi by 3. So I am updating it to pi by 3. Right, on qubit 0. So they have done on the first qubit q0. So I have taken, and what they are asking is, run the circuit and view the state vector visualization. Let us see the state vector visualization. So state vector visualization, if you see here, right, so 00 qubit is more than 0.8 amplitude and 001 is more than 0.4 amplitude. So this is the state vector representation of this thing. So now let us go and see the options. So this is not the option, and this is the C. 0.8 was 000 and 001 0.4. This is the correct answer. So many solutions in YouTube they have given this one, which is the wrong answer. Next, question number 6. Here we are going to see create a 3-qubit state by applying a HUD gate. HUD gate Q on Q0 followed by C0 gate from Q0 to Q1, Q0 to Q2, and visualize the density matrix. They ask you to visualize the density matrix, right? And for this they have given already workbook here, right? If we click here, we will redirect to the following workbook. And here first the installation of Qiskit has to be done, and here they have given the prescribed format, and I have written the code. What was the thing we have to take? How many qubits they here he asked it for us is 3-qubit mission, right? So as we are taking 3-qubit state, so we are taking 3-qubit state here. So the quantum circuit we have taken is 3 qubits. Now first gate we are going to apply a HUD gate, and followed by that control NOT gate from control NOT gate is represented by CX. Control NOT gate from 0 qubit to first qubit, and control NOT gate from 0 qubit to second qubit. So we have done, and now this is the we are drawing the circuit and following density matrix we are going to see. This is the circuit, HUD gate followed by the NOT gate, control NOT and control NOT, and finally if you see, this is the thing. Real amplitude is, this was the diagram, and imaginary amplitude is, this is the diagram. So now if you observe here, it matches the first option. right? And the next one, starting with initial state, they have given the initial state as I, right? So 1 by 2 0 0. So this is the probability. What they have given is, so they have given psi which is applicable on all the, so so the entanglement is on all the qubits they have given psi. So apply a C naught gate with the control qubit Q naught and a target qubit Q1 followed by a Hadamard gate and Q naught. What is the resultant quantum state? So here if you observe that we are going to take a 2 qubit machine, and the 2 qubit machine should have a started initial state with a psi. So this is a 2 qubit with the initial state psi. So what we are going to do is, so here we are going to take a 2 qubit quantum circuit, right? And in order to get this psi state, we are going to apply Hadamard gate. If we apply Hadamard gate on both the qubits, we will get this initial state, right? So applying Hadamard gate on 2 qubits, we have got the first initial state. And next what they asked is, apply a C naught gate with the control qubit on Q naught and target qubit on Q1. So C naught gate, control target on control on zero qubit and target on 1 qubit, right? And next followed by Hadamard gate on Q naught. So again we are going to write it for Hadamard gate on Q naught, right? This is the thing. And finally we have got the solution here, root 2 by 2 0 0 and root 2 by 2 1 0. So qubit 0 0 and 1 0. So this is the second one is the solution. Next apply rotation gate R by 2 by 3 to the first qubit and follow the C naught qubit. So for this also we had the solution here, right? So QC quantum circuit 3, so QCR by rotational gate by, so we are applying, and control not gate we are applying, and finally this is the circuit and this is the solution. 1 by root 2 triple 0 first qubit and 3 by 2 0 double 1. So if you see here, this is the first option. Next, in a quantum teleportation protocol, Bob applies correction on the 2 qubit classical message from LS. If Bob's gate sequence in fourth trial are II, Zi, Xi and Xzi are the corresponding 2 bits message LSN. So now here what we are going to see is I means identical which is taken as 0 0 state, Z means 1 0 state, X means 0 1 state, and Xz means 1 1 state. We are simply neglecting the second qubit I. So the option matches here is the second option. And finally we are going to see the last question. Alice and Bob shows an entangled state and 1 by root 2 0 1 plus 1 0. So here the bases are now 0 0 and 1 1. So if Alice measured her qubit in the computational basis and obtained the results at 0, what is the state of Bob's qubit alignment? The answer is cat 1. So